So it's a great pleasure to have Honglei speaking here, and she will talk about the weekly to algebra of multiplicative forms on a quasi-Poisson report.
Okay, thank you for the invitation. Then I will share my screen.
Yes, great. Yes.
One minute. Okay. Okay, is it okay?
Yes, it's great.
Okay, now start. Thanks very much for the invitation, and it's my great pleasure to talk in this workshop. And today, my topic is the weak little algebra of multiplicative forms on a quasi-Poisson group. You see, I have three information in my title. The first one is like higher structure, a little algebra. And the second one is multiplicative form. I will use MF for abbreviation. And the third is quasi-Poisson group. So it's like we know for a Poisson manifold M with a Poisson structure P, we know on the base of one form, we have a Lie bracket. This is one known. So this work is just a generalization of our classical result. Okay, this is joint work with Georgian and Zhang Liu. Here are some references if you are not familiar with multiplication structures. The first one is about multiplicative vector fields of group lines. And the second one is about forms. And the third one is about tensors. And this one is also about forms. And this is a review paper on multiplicativity. And our work is mostly motivated from the last three references. They are all about higher structures like little algebras on multiplicative vector fields on group 1. So okay, and this one like has a larger framework. You will see. I will mention this in my paper, in this work. Here is a plan. First, of the little algebra on vector field, and then part 2 is the little algebra structure of form. And the part 3 is the infinitesimal result. Okay. And here our part 3 is independent of part 2. And in the last part, which is the combine or relate part 2 and part 3. This talk is based on the 3 works which are posted on our. Okay, part 1. Payback field of a given point is multiplicative if the graph of a group find multiplication is co-isotropic, sum manifold of T3. So this is a geometric description. If we unravel this co-isotropic condition, we will get the algebraic description. This is an equivalent definition. Let's see. The first one is the value of pi at gr equals the left translation of pi r plus the right translation of pi g minus here x is, if this is g, this is r, and this point is x. It's a target of r and source of g. And this condition is also called a fine condition. So okay, here bt and br are bisections, local bisections passing through T and R. Okay, this condition is equivalent to that the Gaussian bracket of pi with the right invariant vector field is again right invariant. So that we get a map from gamma A, which is the section, and to K to gamma vector A because this pi is the k vector fields. Okay. The second condition is that the Gaussian bracket of pi with t star f, t is the target, is again right invariant, which means this del pi can also act on functions of the base manifold. And the last condition is that the M is co-isotropic. Also, the restriction of pi on M, the base manifold, has no component in wedge A. Okay. And we have another definition just for you to understand this, understand multiplicative vector fields. The last one is that if G is a coupon, then we know the tangent bundle and cotangent bundle are both coupon. And our K vector field sends K minus 1 forms to a vector field. So pi is multiplicative if and only if this pi sharp is a coupon multiple. So this definition, these are three definitions for this multiplicative vector fields. Okay. Okay, let's record the definition of D2 algebra. D2 algebra is the categorification of the algebras. And here I use actually the definition of two-term unity algebra. It has the data. First, this is a linear map between two linear spaces, G minus 1, G0, and also two brackets, which maps G0, G0 to G0, and also G0, G minus 1 to G minus 1. And also we have a three bracket, which maps Y3, G0 to G minus 1. It satisfies the following condition. The first one is the compatibility of B and the two brackets. And the 2 and 3 are like we call generalized the Jaffe identity. It means the Jaffe identity of the two brackets does not satisfy, but they are hold up to the three brackets. Okay. The last one is cocycle condition. If this T0 is a Lie algebra, T minus 1 is a module, then this one means the three bracket is a cocycle. It has 10 terms. And also we can see this is the compatibility of the two bracket and three bracket. Okay. If this three bracket vanishes, then this B2 algebra is called a strict B2 algebra. And in this case, because there's no three bracket, so G0, in this case, we know G0 is a Lie algebra. And the G minus 1 is a G0 module. And we still need the condition 1. We still need the condition 1. Okay. So also for this reason, we always denote the two brackets of G0, G max 1, which value of G max 1 as using this action notation. Okay, a homomorphism between two Lie algebras has zero maps. The first one is F0, the second one is F1. They are a train map. And we also have a homotopy map called F2, which is from Y2 T0 to G minus 1 5. And that is according to condition. It means actually this F0, 1, preserve the two brackets and the three brackets only up to the homotopy term of F2. Okay, now the result is that, okay, that's, I still need a result. One example of multiplicative L vector field is that if tau is the L section, A is the L5, then the difference of the right translation and the left translation is automatically multiplication. Okay, then we have a map from section of A to temperature vector fields. And we'll see this is a strict graded literal algebra. And here, by graded literal algebra, I mean this G minus 1, G0, they are graded vector space and graded Lie algebra. Okay, graded Lie algebra model. And then here, the two bracket on multiplicative vector field is just the Gaussian bracket. And we also need an action of this multiplicative vector fields on sections. This is actually guaranteed by the multiplicativity because we know that we have this third pi. We have this third pi. This is pi, this is tau, and because the Gaussian bracket of pi with left translation is with right, invariant vector field is again right invariant. So we have a well-defined method, third pi here. And here I will emphasize that for the start equals 1 case, I will refer to more earlier work of Brahic, Lemon, and also Artist works. Actually, this little algebra plays important roles in their works. Because the homotopy equivalence class of this little algebra is Morita equivalent. So the equivalence class can be considered as multi-vector field on the corresponding differentiable stack. And in short, it means this little algebra is actually used to define vector fields on differentiable stack. Okay. Now we have the question. So since on vector field we have this little algebra, so do we have one on multiplicative forms? In general, on forms of little points, there is no bracket. So for this reason, we consider Poisson group point. We consider Poisson group point and also positive Poisson group point. That's the motivation of our work. Are you okay? Do you have some questions? I'll finish my part 1 at this moment.
I think we're all good.
Okay. Okay, then I will continue. A K-form is multiplicative if it satisfies this condition. Here M, PR1, PR2 are all mapped from G2 to G. M is the point of multiplication. PR1 and PR2 are two natural projections. So using pullback, the 3 terms are all formed on G2. Okay. The definition looks more clear than the definition of multiplicative vector fields. So also we need to record the Poisson group points. Once we have a Poisson structure, we will have brackets of form. A Poisson group point is a group point with a bi-vector field, which is multiplicative and also Poisson. Then on the one form, we have a Lie bracket. It's well known. The factor multiplicative one form closed with respect to this bracket? The answer is yes, and we can develop the Gaussian calculus on multiplicative vector fields and forms. And actually, both the contraction and the differential preserve the multiplicativity. Okay. Now let's extend the Lie bracket to all forms, not just on one form. And then we have Poisson bracket on all forms. It has this. Actually, it is the BD algebra. It's an exact exact BV algebra. Exact first-order algebra or also BV algebra. And the P bracket has this form. Here, LP. Here, this LP is defined by the contraction of P and composed with differential. So differential lowers degree by 1, increases degree by 1, and the contraction lowers the degree by 2. So altogether, we lower the degree by 1. Okay. So the question is, are all multiplicative forms closed with respect to the causal bracket? Actually, this is not obvious. This is not obvious because multiplicative forms are not closed dependent on what. Means from this is not obvious because if alpha is multiplicative, beta is multiplicative, then the wedge product is not multiplicative. So, but the answer is yes. We proved this. We proved this result by tedious and but quite elementary calculation. But I'm wondering if there is a conceptual proof. If there must be some conceptual proof to see why the multiplicative forms are closed with respect to this causal bracket. Please let me know if you have some ideas. Thank you very much. Okay. Okay, here's our theorem. For Poisson group point, in this case, there's no bracket strict graded into algebra. You see here on form, we have this, let's say, this causal bracket. And here the mapping. Okay, here I have to say if gamma is a L form on M on the base manifold, then like the difference of left translation and right translation, then the difference of the pullback of the source map and the target map is automatically multiplicative. Okay, so we have this map. And also because of the multiplicativity, the causal bracket of theta with the star gamma is again of the form sum of some form. So then we define an action of theta and gamma. The formula is very similar to the one in multiplicative vector fields. The idea is the same. And moreover, this Poisson defines a strict D2 algebra homomorphism between the one here on the form and the one on multiplicative vector fields in part 1. Okay. So our next question, what about quasi Poisson points? Can we get weak D2 algebras like the through bracket appears? Here we have two motivations to ask this question. The first one is like generalization. Poisson to Poisson, Poisson to quasi-Poisson, strict to weak. Here I use weak just for axis. Generalization. The second motivation is that, and actually the Morita equivalent of let me just write it down, like Poisson stack. And actually the Morita equivalent of quasi-Poisson points. Actually, let me repeat, the isomorphic of Poisson structures on stack are actually Morita equivalent classes of quasi-Poisson points. So in this way, this is the result of the work I mentioned in the reference of Ping's work. And because of this result, the quasi-Poisson points, to study the case of quasi-Poisson points is natural and also important if we want to study Poisson structures on differentiable stack. Okay, what is the quasi-Poisson coupon? It is a coupon with a bivector field which is multiplicative, but it is not Poisson. The Gaussian bracket is controlled by the difference of right invariant vector field of left invariant vector field given by the reflection of A. And the second one is the compatibility of P with the right invariant vector field generated by phi. And in this case, because P is not Poisson, so the bracket of one form is not a knee bracket. Let's see two important formulas. Like the Geometria identity is not zero, but it's controlled by PP in this way. It has four terms on the right hand side. The next is P sharp does not preserve because P sharp is a map from forms to vector fields. It does not preserve two bracket up to this term. So actually, at the moment, we can get a weak V2 algebra space right here. The two bracket is as before, the P bracket. And this condition will guarantee the generalized Geometria identity of the V2 algebra. Generalized Geometria identity. And this condition will make sure the compatibility of the two bracket and the zero bracket in the V2 algebra, and actually this phi will be the zero bracket. Let's see the detail. Okay, I forgot to mention, like in the Poisson case, the dot equals 1 case is zero by Oliver's work. Okay, here for causing Poisson coupon, the complex is as before, the two bracket and the action are as before. We define the third bracket in this way, and actually this is just part of the right hand side. Okay, so we know the two brackets and the zero bracket, the compatibility is controlled by the condition of P phi equals 0. Okay, since phi defines the zero bracket and P defines the two bracket, but in which way? Here's the relation. Inside of the bracket, this is the compatibility of or actually the conductor condition in the V2 algebra. And the left hand side, first we make the gap that this one would equal to this term, but no, it has a lot of terms, and finally we discovered that it has another like 4 terms. Okay, this way. So this is the difficulty of the proof of the theorem. So if this P phi is 0, we can see we will get the condition we need for V2 algebra. Okay. And so now we move to all forms. Okay, the complex is as before, the two brackets is as before, the Poisson bracket, and the action is defined as before. Here for the third bracket, we cannot use because the white product, because the multiplicativity is not preserved by the white product, we just cannot. We cannot use a Leibniz rule to extend the zero bracket in my previous slide. We have to define it directly. Okay, let me explain this bracket a little bit. Here, this one is the P form. is 2 is a Q form. This is 3 is S form. So the third bracket S star, the third bracket is valued in a form in the base manifold. So S star will be a form on the leading point. How do we define it? Here, phi is our reduction of A. So the left translation, this is a 3 vector field on G. So here my contraction is just the contraction of one vector field with a 1 form. So finally we will get a tensor form here. So the second layer of contraction is again, this is the form, this is the tensor. The second layer of contraction is again the contraction of one vector field in the form. So 3 layers of contraction will finally will only have formed the 3 vector field. The 3 vector field disappears. So altogether we will get our form. The degree of our form is lowered by 3, and then a differential increases the degree by 1. So altogether we lower the degree by 2. So this is exactly what we need here. But we still need to prove this bracket is very fine. Okay. The second part is this is a weak E2 algebra here. This is a weak E2 algebra, has 3 brackets, and on the right hand side, this is again the E2 algebra in part 1 we record. So our quasi-Poisson defines a weak model between these 2 algebra. Here, this homotopy term is defined by this our phi. Okay, in the quasi-Poisson point. Okay, this is our main theorem. Here, let me explain a little bit of the contraction here. And the contraction of a tensor field with a form is just the contraction of a one vector field with form. And the lemma is this contraction preserves the multiplicativity. Okay. And the second one is the contraction of a theta multiplicative.
Hello?
Which is the quotient. Graded algebra, this is graded algebra, and this is graded algebra. And also quasi-Poisson Poisson structure P sharp gives a graded algebra. You can see the difference of this bracket is exact, just the value in this quotient space. So for this one, we get information on step, and actually this part is just the forms on step. Let me just use step. Let me just use gamma. This one is the stack vector field on stack and quasi-Poisson structure. This is the Poisson structure on stack. So the consequence of this theorem. So from this theorem, from our main theorem, we get the result, the corresponding. So we know the result on Poisson manifolds we generalize this result to differential stack. Okay. Let's see some example. Look of multiplicativity. we can see like there are only non-trivial multiplicative one forms on the groups. There are no higher multiplicative forms. Okay, so given a quasi Poissonian group, since there is no base manifold, the multiplicative one form actually in this case it is a linear algebra. It is actually isomorphic to the G-invariant elements of G star with a star bracket on G star. We know G star is not a linear, it's quasi case, it's not a linear algebra. But the G-invariant elements consist of this algebra. Okay, and this one is on the vector field. We still have the Li2L. We still have strict Li2 algebra on the vector field side. So since this is a quasi Poisson case, we have a weak modulus. We have this is defined by phi. So this is a weak modulus between two strict Li2 algebra. Another example is linear quasi Poisson phi. Given linear algebra, we know the dual of the linear algebra is the linear Poisson group. So the dual of the Li2 algebra, is the quasi Poisson two function, actually is the quasi Poisson two group. Okay, here let's see the dual. The group one, it is actually an action group one. The action here, this is a base manifold. This is M, this is G. Okay, so the action is given by the linear map. This is D dual. Okay. This is an action group one. For this group one, we can write down explicitly the multiplicative one form and also multiplicative one vector field. And applying our theorem, we have two weak Li2 algebras and a weak homomorphism between these two algebras, these two Li2 algebras. But you can see this is infinite dimensional and also quite complicated. So because it also has the ability group structure on this point, it is a two groups. It has group point structure and also group structure. So we can consider vector fields and also forms that are multiplicative with respect to both the group one and also the group structures. Okay, then we should be for both. Then this base will be this condition, this will be very restrictive. Okay, so finally the one form is G0 and the vector field. The vector field is N0 G0. Okay. So the Li2 algebra modulus is just G is okay. This is G0, and then also we consider linear. The linear one forms on okay. Okay, I'll just write down this one. Okay, here we consider B. It's B, both multiplied. And here we consider, because M is also a group, we consider this linear one form. Then we will come up with the G. And then the right hand side is the one on like gamma A, we'll consider linear section. And here we consider this B multiplicative. And we get, actually we'll get the joint. This one is this is obvious in the algebra. You can see in the algebra, if G is the linear algebra, G star is the linear Poisson structure. Then the Poisson structure gives the map from vector fields on G star to form to one form on G star to one vector field on G star. And if we consider this linear, this is G, this is G, and this will be in G star, and this P sharp will have this P sharp will be a D star, the co-control. Okay, now let's move to part 3, the infinitesimal level. Because we know the universal lifting theorem, if we have this little algebra structure of multiplicative forms, then we must have a little algebra of infinitesimal multiplication one forms on the algebra. But here we want to write it down explicitly. That's one reason. Another reason is that we cannot believe that the bracket on this infinitesimal level must be easier to understand. Okay, let's see. Okay, the infinitesimal quasi-Poisson point is Cauchy bi-algebraic, and the infinitesimal multiplicative K vector field is K differential from A algebraic, and here we have our infinitesimal multiplicative K form on the algebraic. Okay. So Cauchy bi-algebraic is a triple. Here A is the Lie algebraic, and phi is the 3 section, and D star is the degree 1 derivation with respect to the wedge product from gamma A to gamma wedge to A, satisfying the following 3 conditions. The first one is D star is like a cosine condition. The second one is D star squared is not 0 but controlled by phi. And third one is D star phi is 0. So this D star, actually the dual of D star will give a bracket on A star. Since D star is squared is not 0, so this is not a D bracket. And also D star can have some functional, and we also have the anchor. Okay, this is the structure on A star. And I am one form. Here we only have the results for I am one form. I am one form on the algebraic is a pair where mu is the bundle map from A to T star m. Theta is an element in A star. Here T is differential of the algebraic A. So theta is a gamma A star. So this is true gamma A star. So X on 2 elements in A. This one is valued in T star m. This is anchor. Okay, the second one is mu X on the Lie bracket. So this is the mu, this is theta. Our theorem is that given a Cauchy bi-algebra, we have a little algebra. This is a weak little algebra. So this is kind of well known that given one form of M, this one will give an infinitesimal multiplication one form on the algebraic A. Okay, and let's see the 2 bracket. Let's have a look at the 2 bracket. Where mu is like a bundle map from A to T star F. Let me write as a whole A to T star F. Okay, remember that because the A star we have this anchor. So the dual, rho star, the dual will valued in A. Valued in A. So look at here. This one is kind of the bracket of this part is kind of like the commutator. We'll use mu rho star and composed with this is like a commutator. So this is actually a D bracket on this part. Okay, commutator. Let me use C to denote it. And the second one is on theta. The bracket on theta gamma A star is just the bracket on A star. It is not Li, but there's a two bracket here. And actually we have like, it's a semi-direct product, which is valued in this part. Okay, this is the structure. And we can define the action. And also the third bracket in this case is defined by phi. This is like easier than the in Google points. Okay. And here the complicated part to prove this theorem is to check like the infinitesimal multiplicative one forms are closed with respect to these two brackets, which is to prove it directly. This part 3 is independent of part 2. Okay, we just start from a Cauchy bialgebra. Okay, we'll use like a lot of properties of a Cauchy bialgebra. Okay. And like before, we'll have a little algebra homomorph. This is phi 0. Okay, it has this form, and psi 2 is given by phi. Okay, and for the Cauchy bialgebra, we have this form. Here, this is 8 given by 8 star. We have phi here. Okay. Okay, here, let me just relate the result in the previous slide with linear one form on vector bundle. Given a Cauchy bialgebra, the bracket on A star actually gives a linear two vector field on A. This is not Poisson, but there's a two vector field on A. If we have a two vector field, then we can have a map from forms of A to one vector field on A, which is given by this PA sharp. And because this is linear, actually this map sends linear one form this vector bundle A to linear vector field vector bundle A. And actually, why do I say it like this? Why do I mention this one? Because the space we just studied in the previous slide, this IM one form on A is like a subspace of this one. This is our third differential. It's a subspace of A. And remember, we have like a 0 here. And the result is that here we have a two bracket, and we have this two bracket here. And we'll see the bracket which is mentioning our theorem of part 3, that this bracket, this is just a sub algebra, not a sub here. So this phi 0 in some sense is also Poisson restriction of Poisson. This tells us where the two brackets comes from. It's actually just the restriction of this bracket is also the Poisson structure of one form. Okay, here's the result. This is the one I mentioned before, and the studied here. What we studied here, this is just the subspace. Also, every horizontal map preserves the relevant bracket. And this one, 10 in the literature, also has a nice description. If you are interested in this linear one form, here are the two references for linear one forms and linear vector fields on vector bundles. You can find them in these two references. Okay, the last part is let's relate part 2 to part 3. Okay. If G is as connected and simply connected, we have two one-to-one correspondence. These two theorems are called universal Lipton theorem. Okay, the first one is multiplicative one vector field on G to one differential on A, and given this way. And the second one is the one correspondence between multiplicative one forms on G to infinitesimal multiplicative one forms on the algebraic. They are this maps are defined clearly. And the proposition is that if G is a Cauchy group point, Cauchy Poisson group point, A is the corresponding Cauchy bi-algebraic, and then this map on the group point level, this is psi zero. This is on the infinitesimal level. If G is connected and simply connected, then that's just isomorphic. And also the Lie2 algebra, actually, this is the Lie2 algebra we have in part 2. And this is the Lie2 algebra in part 3. We just define them directly. And if G is as connected and simply connected with two Lie2 algebras, that's actually isomorphism. Okay. This is isomorph. Okay, here I will summarize my result in this last slide. And look at this is like a big commutative diagram. Look at the front face. This is like our result in part 2. We have like with Lie2 algebra on multiplicative one forms, and the Cauchy Poisson structure defines a weak morphism between the Lie2 algebra forms to the one on vector fields. Okay, and also the back face of this big diagram is the resulting part 3, like the corresponding result in the infinitesimal level. And the left hand right faces are the isomorphisms between them if this G is connected and as connected as simply connected. Okay, this is all my talk. Thanks for your attention.
Thank you. Let me see if the audience has questions.
Okay.
Okay, one question is about the behavior of life. Yeah, so I think you mentioned that it's pretty good. So one question is about the invariance of this Lie2 algebra that you constructed on quasi-Poisson reports. I think you mentioned that.
Let me go back here. So the question is whether this Lie2 algebra is invariant, right? Is this the question?
Yes.
And we didn't prove it, but I think the answer is yes. We haven't proved it. We didn't prove it in our paper, I think, but I guess the answer is yes. Okay.
Yeah, can you go back to your, not the very last, the previous slide, the one before the very last one? Thank you.
Okay.
So I was just wondering, is there like a version of that for the higher degree forms and multi-vector fields? So why is it only written for degree 1?
Okay, and because yeah, there are like the corresponding results here, but
Yeah.
I need some more time to write it down because for the one form, the proof is already very complicated. So to prove the general case, it becomes very, very complicated. So I think there must be some like conceptual proof that I haven't figured out. So this is the result so far. So okay, like the part 3, I only have like the 1. Yeah.
And I was just wondering, for part 2, the way you guessed these formulas for the infinitesimal lead to algebra, was it by differentiating what you had, or you had another way of, finding them? They look kind of intricate.
Yes. So here for the one case, we just make the guess and then prove it's the infinitesimal, it's the differential of the bracket on forms. Yeah. So for general case, actually, I haven't tried to differentiate directly. Like I don't know if this is like obvious for you. Like, see, let me show you this bracket. Okay, this is the bracket on one form. So I don't know if this is like obvious for you. Like this is the differential of this is the differential just of the P bracket. Not obvious, right? So please let me know if you can see this, directly.
This point of view of functions. I mean, when you study the tensors on this big group point, you can see them as linear functions. And maybe, I don't know, for example, this map that you have from one forms on M to forms of a group point. You can see these as somehow the source minus the targets. Yeah, I don't know.
Yeah, I'm not. It's not very clear, so I didn't understand. Yes. Can you repeat?
Yeah.
Like.
I think you're just mentioning that one can see multiplicative forms and multiplicative multivector views as functions on other points which are T and T star, right? If this point of view is
Yeah, okay, thanks very much. So yeah, I know that. Yeah, maybe, okay, like this result, like there's a more general framework for this higher structures, right? Like, yeah, okay, I haven't thought about it in this way. Okay, thank you very much. Yeah. Like I know to define this multiplicative tensor field is used the group point as functions as multiplicative functions are larger group point. Yeah, I haven't understood this B12 in this framework. Okay, I will try. Thank you.
So if there are no more questions, we can thank the speaker again. Thank you very much for the nice talk. I hope it's not too late for you. What time is it there?
Yeah, it's 9. It's 9 p.m.
Well, thank you again.
Thank you, Enrique. First of all, I would like to thank Clarisse, Christian, and Jean for organizing this event and obviously inviting me to give this talk. So maybe I want to start with just giving you some general ideas on what I want to talk about, but being very vague about what I'm saying, okay? So there's a situation, rather common situation where you have some kind of vibration. I'm going to put some quotes, and it comes with some structural group or some kind of a structure, right? That has symmetries, and so it could be a group, a two group, okay? So maybe some more quotes here. So you can think of principal bundles, principal two bundles, these kind of things. There are Q bundles. What do you put here? Like non-abelian gerbs. So this sort of things, okay? So you have your vibration, and then you're going to choose some trivializations. Or some sort of splitting. Yeah. Sometimes both. Okay. And so the output of this would be, so here I'm gonna take two different paths. So usually you can get some sort of characteristic classes. So there are characteristic classes for principal bundles, for Q bundles, non-abelian gerbs too. So here, and the other one is, so you take splittings and you obtain connection, curvature, etc. So you have some sort of some fields. Okay. Again, I'm trying to keep very vague about what I'm talking about. Okay, and so here I would be interested in. Okay. First, concrete examples of this. Yeah, and we would like to have some kind of interpretation for these characteristic classes. Okay, so this side here is kind of contravariant. Yeah. So if you think of Chern-Weil, okay. So basically you. So you have classes in your classifying space, and you pull them back, and you obtain a class here. Okay, and so this side here is more covariant. Because so you have connection, curvature. So you want to take, higher path, holonomy, holonomy. Oh, okay. Okay. And so the question is how to really relate these two sides of things. Okay. And really, so here is more cohomological. Okay. And here is more homotopy. And so this side of things is much better understood. There are many constructions, so we kind of know how this works. The interpretation is more complicated. This one that involves homotopy, higher homotopy, is much more complicated. And so what I want to do today is, in a very simple example, try to relate some cohomology classes with some kind of a homotopy theory. And the link is done by this higher holonomy. And basically, higher holonomy is done by integrating stuff. So basically, you have a cohomology class, some path you pull back, and we're going to integrate. But this is interpreted in terms of this higher holonomy. Okay. So, as I say, that very vague ideas, but I hope it conveys the the general picture of what I want to talk about. Okay. So let me start with transitively algebraics. And I want to relate this with these Yang-Mills things. Okay, so if you start with a transitively algebraic, so you have your anchor map that is surjective. You take the kernel of the anchor map, and this defines the bundle of Lie algebra. Which are the isotropy. Okay, and so if you want to understand a little bit better your transitively algebraic, you just choose a splitting. I'm going to call the splitting S. And so the splitting kind of allows you to decompose the structure. Okay. Okay. So the splitting is going to use two things. Okay. First, a connection. So the connection, I would write it as a one form on M with values in the derivation of the Lie algebra, the bundle of Lie algebras, and then some kind of curvature, which is a two form on M with values in my bundle of Lie algebra. So here I put a small m just to figure that it fibers over M. So that's basically my fibration. Right. Now, so one form, two form, one with values in derivation, the other one with values in G. And let me point out that there is a map from sections of G to the derivations of G. So just to make things clear, maybe what I call a derivation so this is something that goes from sections to sections. Okay, so that this is what's linear. And this is the derivation of the brackets. We call it D and D. Maybe I can do this. Okay, something like this. And so these derivations are actually the sections of a Lie algebroid, which I also denote by der. Okay, and they are just derivations of the bracket because, see, did I write something wrong? What did I do? It's no, because of this it comes with it's a very good question. Thank you for asking. Because of this property, it comes with a symbol. Okay, so there's an anchor map, and so you know this guy is locally trivial. So this one is transitive as well. So basically, what's going on is you have your connection. It has values in derivation, so you can trivialize using the holonomy. I'm going to talk about this. Okay, but indeed, no. So when there are the C infinity ones, I'm going to write with a small d. Yeah, the big D and the small d's. Okay. So how are they don't? So let me. So it's something like this. You just take the bracket in A. So maybe psi. So this is defined. So you just apply your section psi. So here I use the bracket in A. Take a vector field. I apply my section, and then I can bracket with an element in the isotropy. And this defines the section of the isotropy. And omega, I want to write it like this. So this would be up to sine. SS, sorry, I'm used to say S, and then S. Yeah. So you take, so this would be the bracket in Tm, and here this is the bracket in A. And the difference takes values in the isotropy, in the kernel of the anchor. Yeah. Right. Now these satisfy some conditions. Okay. And okay, and again, I want to keep this equation here. The equations that are satisfied are that, so the curvature of the connection like this. So this is called the inner curvature condition. And this is one. Then I will have two. Another one. So the covariant derivative of omega with respect to nabla is 0. So this equality here, what is this? So this holds into, they can do this. So these are two forms with values in derivations. Okay. Because some bracketing, nabla has values in derivation. This is bracket of derivation. So this is, okay. And you see that omega takes values in the Lie algebra. So I have two forms with values in this guy. So I can apply the add map in order to obtain a two form with values in derivation. As it turns out, you see this add map takes values in vertical derivation. So the symbol is trivial. So that would actually take values in smaller, right? But let's forget about it, okay? And this is, so nabla is a two form. I applied the covariant derivative. So this is a free form on M with values in G. So there are some gradings that I don't really want to talk about, but you see, one form with values in this, two form. So both of them are kind of homogeneous, and then this map here. Okay. So these are the structural equations. And so one thing you can do is choose another splitting. So I'm going to choose S. Okay. And so if you have two splittings, oh, now they differ by one form with values in G. Okay. So these are like gauge transformations. So let me call gamma the difference of two different splittings. So this is a one form with values in G. Then, in fact, the difference of the two connections induced by S and S prime is going to be given by head composed with my gauge transformation and omega minus omega prime is going to be, so there's a formula nabla gamma plus something like this, gamma. Okay. B. Okay. So again, this is a one form with values in G and two form with derivation, sorry. And this is, all right. Okay. Sorry? Yes, on M, because I think. All right. Okay. So all these objects, I see them as covariant, like nabla in omega, because you see the nabla goes from Tm to there. Okay. So, and I see this as something that pushes it inside the structure group. All right. Okay. Right. So this process can be reversed. Okay. So if you take a connection that is so compatible with the Lie algebra structure, a two form with values in G, you can reconstruct original Lie algebroid, or reciprocally. Nabla. So if you couple satisfying 1 and 2, then you can somehow reconstruct A, which would be just, you take the direct sum, and you cook up just a project, and so on. So this is, this process is somehow reversible. And if you choose some gamma, which is a gauge transformation, you obtain you can define an automorphism of this. Okay. So this is quite standard. And so I'm going to rephrase this in a slightly different way. Yeah. But I will basically always start with a connection and omega, okay, and think that it comes from a splitting. So that would be the first interpretation of this. Okay, this I can erase. Up. Okay. So what's at least the first interpretation? And that would be a theorem, actually. So that would say that kind of structural theorem. So if you take a pair nabla and omega like this, satisfying the two structural equations, 1 and 2. So this is the same thing, okay, as having a L infinity map, which is actually given by nabla and omega. I'm just interpreting those as a L infinity map. Okay, like this. So this defines a two algebra. Actually, well, a two algebra, it should be. But then there's a L infinity map, L infinity algebra structure here. This is L infinity, but putting some trivial term here. Okay. And so if you don't know what is a L infinity algebra or L infinity map, it doesn't really matter because this is exactly this. So in the previous talk, actually, these appeared. Okay. So it was something like this. So in the previous talk appeared something, and there would be up. Okay. So the main idea is the following. Okay, at least I can say that. So if I take sections, here I have vector fields and here I have derivations. So nabla it doesn't preserve the Lie bracket on both sides. Okay. So this is the difference here is not 0. However, this is omega. Okay. So the difference, the lack of being a Lie algebra map is still controlled by omega. And in this L infinity world, it doesn't matter that it's not a Lie algebra because it's under control, and omega is part of the morphism. Okay, and then there's this extra condition. So these are strict true algebra. In the previous talk, they were not strict. So this is nice. In fact, so I thought, so now I can see a transitively algebra together with the section as just an. And as I mentioned, or maybe I can do two different splittings, transformation, and this also fits into this picture. And so it looks like this. Gauge transformations. So it would be, so let me put my map like this. So, yeah. So I would have, nabla, omega, and here nabla prime, omega prime. Okay. And so the gauge transformation define okay. Okay. And so we can bundle all these equations in these kinds of diagrams. Okay. Are there questions so far? Okay. So now what I want to do is get rid of this equation. Okay. So I want to start with the same step, which is a connection, a bundle of the algebra, a compatible connection that has inner curvature, but the true form that makes this curvature inner might not be closed. Yeah. So let me at least motivate a little bit. So, Olivier, why are you doing this? Okay. Oh. Okay. So there's this. So there's these things that comes from physics, which is in order to describe the dynamics of a particle in the Young-Mills fields. Okay. So how this relates with this picture is basically by dualizing. Okay. So dualizing this picture. So because I have a splitting, I also have a projection from here to here, and I can take the dual in order to obtain a map from now the dual of the Lie algebra with values in A star. Okay. So now this comes with some structure, and I can pull back the Poisson structure to a structure here. Okay. So this pulls back the Poisson structure. So the pullback is not Poisson, but it's Dirac. Okay. Okay. And now I have a Poisson Dirac structure, sorry, on the dual of my bundle of the algebras. Okay. And how this relates with physics? Maybe I will keep this. So the idea is something like this. So you have here your bundle of the algebras, your projection. So you have to think that you have a particle that is moving into M. So here you have a point M, and that's your particle moving around. Okay, but the particle comes with some internal symmetries. Okay. Yeah. And what models these internal symmetries are the dual of the Lie algebra. Okay. So here I want to put, the dual of the Lie algebra. Okay. And this is Poisson. Okay. It's linear Poisson. And the leaves here are the coordinate orbits. Okay. And physically, what are these leaves represent some different states of your particle. There's something you see when it's moving. So it's this quantum thing that you cannot measure. And each coordinate orbit represents a certain state. So you have to think energy, some periods, what happens is that you cannot move from one state to another unless you put a lot of energy, okay? Because it's basically breaking your particle from moving from one state to another, okay? And this behavior of low energy that doesn't break your internal state is bundled into the Dirac structure. This is because, so here I would have another point, so my particle maybe moves from here to here. Yeah. And so the leaves of the Dirac structure here not only contain the conjoint orbit, but there's a horizontal part, okay, that allows you to move from one place to another, okay? But if you move around, your particle cannot go, you know, from one conjoint orbit to another. This is prohibited because you don't want to break your particle. And so this comes exactly from this, because the curvature being inner just forces whatever trajectory you have in here to preserve each conjoint orbit and therefore each state. Okay, so locally. So there are two things, okay? So if you don't care about the Dirac structures and just think of the physics, and you just want a model that would preserve internal states, you don't really care about that. The only thing you want is this. That's the first thing. The other one, and I just want to write these equations locally. And the other one is the omega plus alpha omega equals 0, 1, and 2. So this is just writing this in terms of, I mean, locally. Okay. So alpha would be the one connection form, and so it would be called a gauge field in physics. And omega, so this bends, but it's called like magnetic term. Okay. And what happens is that you can start to write things down locally, okay? And so you can have a, so you have your connection and you make it inner, choosing some omega. But if you try to glue all these local data globally, there's no reason for this to happen. Okay. So it's kind of natural to get rid of this. And it's exactly the way, you know, this West Sumino term appear when you try to glue local data globally. So kind of a motivation for doing this. Check the time. And so why one would like to do this is basically, that was the original. So it's another motivation. Okay, I'm switching topics a little bit. So Mackenzie was interested, you know, if you take a principal bundle, okay, and which you can think as a transitive groupoid, the associated bundle, which is just the isotropy, this is abstracted. So this is a locally trivial bundle of group, but if you start with a bundle of Lie groups, there's no reason for it to be the associated bundle to a principal bundle. Okay, so there are the topology matters here. Okay, and basically one of the things that can go wrong is exactly this, where you try to glue things together, and there's something global. Okay, so that's enough motivation, enough physics for everyone. Okay. So what I'm saying is that take a bundle or a transitive groupoid. Look at the associated bundle. So here they're associated with the adjoint action. This is abstracted in the sense that, so this is a locally trivial bundle of Lie groups. But if you take bundle of Lie groups, does there exist a principal bundle whose associated bundle is this? In other words, if you start with a bundle of Lie group, is it the isotropy of a transitive groupoid? And the answer is no. Here, what I want to do is kind of the infinitesimal thing, which is, oh, I start with a bundle of Lie algebra, and can I fit it into a transitive Lie algebroid? And I know, because if I have a transitive Lie algebroid, I take a splitting, I have a connection form, I have these two equations satisfied, and I'm basically assuming, oh, I'm halfway there, right? I'm assuming that the curvature is inner, but I'm not assuming this a priori. So can I correct things now in order to fit my, that's the motivation. Okay. So now I can talk about the Mackenzie class. Oh, yeah. Oh. So one of the motivation, sorry, for Mackenzie to study this thing, I think, was also integrability. Sorry. Yes. You would call it Bianchi identity. Yeah. Thing is, Bianchi identity usually is referred, for a principal bundle. But the one form has values in G and the connection has values in G. So, sorry, yeah. Uh-huh.
What happens if you take this, that this is different from zero? Because something different.
I'm going to explain, yeah. But the thing is, a physicist wouldn't really care. I mean, it would work locally and write everything locally. And locally, you can always make this to be zero by integration. The problem is when you globalize everything. But still, the theory will work, kind of. we will make it work. Okay. 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 So, okay, I won't keep these equations. Okay. What's this Mackenzie class? Okay. So now I'm going to start with nabla omega. What? Sorry. I'll be very precise. So a bundle of the algebra, a compatible connection, and then omega. And I'm just going to assume that the curvature is so satisfying only one. Okay. Okay. So here, because the curvature is inner, so you can look at the center of your bundle of the algebras, okay, and you can restrict the connection to the center, okay, because it's an ideal. My connection preserves the Lie bracket, so the connection will leave the center stable, so I can restrict. Z, okay. But if you look at the restriction, okay, because the curvature is inner, so here I have curvature, but it's inner, and the inner automorphism acts trivially on the center, okay. So what this tells you is that the restriction to the center is flat. In other words, when I take holonomy along homotopic path, they induce the same, the restriction to the center is independent of the homotopic class. Okay, so I have a flat connection, and I can use this to define a complex, right? Kind of de Rham complex on forms. So I take forms, z-valued forms, which is given by the covariant derivative. And therefore, I have a cohomology of forms, z-valued forms. Okay. Okay. Right. Now I can start taking care of my two form omega. So here, say I can start with a two form, and I obtain a free form. Okay. Now omega is a two form. It's not z-valued. In fact, if it was z-valued, the connection would be completely flat. Okay. But nabla omega, so this is a free form. Oh, sorry, I write exactly what I want not to be. Okay, so it's not z-valued a priori, but if you look at its covariant derivative, a priori it has values in G, but it turns out this is a free form, and this one is z-valued. Yeah? It's super easy to see because if you take nabla omega, basically you apply add, because nabla preserves is compatible with the Lie algebra structure. This is going to be nabla add omega. Okay. Okay. But add omega, because of 1, is basically the curvature of nabla, of your connection. But now this is Bianchi identity, and we know that this is 0. Okay. So it's kind of straightforward. So now I have a free form with values in Z, and it turns out it's a cosine. Okay. So what I'm going to do is now, okay, I have a Z-valued form, so okay, and I'm going to write nabla omega. This is 0. I don't know computation because it's not straightforward than the other one, but basically, essentially, you can see that, you know, nabla, so nabla of, I mean, it's almost a co-boundary, right? Because it's just that it's not z-valued, okay? But makes it work is essentially this, okay? So the claim, let's put a proposition. Is nabla omega is, let's see, okay, and therefore you obtain a class which is phi, which is in the H3 of M, okay. And this is what is called the Mackenzie class. Okay. Now questions like, so what does it mean that it vanishes? Okay. And the vanishing is something like this. Let me see how I put this. Okay. So say that assume that is some nabla. I want to write D because it's differential, or some beta, where beta is a two form. Okay. Then what I can do is, you know, I can correct. So here I could, you know, I'm going to put nice beta. So beta is z-valued, so I can change omega divides omega by beta, and beta gets killed by add. So I keep this equation, and minus, okay, beta. And now I can kill phi, so I can kill omega by beta. Okay. So this beta actually works as a gauge transformation, or higher gauge transformation, the way you want to call it, because so the proposition is this is a coboundary, and this class is independent. So that would be another proposition. Is so this does not depend on nabla modulo gauge transformation. So that would be omega 1 of m. I think, yeah. Okay, so I can, if I modify my connection with the add map applied to one form with Bayesian G, this doesn't change. Okay, which corresponds to when you choose different splittings for the transitive algebra. The thing is, I don't have a Lie algebra right now. Yep.
So at the very beginning, you gave an interpretation of equation 1 and 2, nabla omega equal to 0, in terms of an infinity map.
Yeah.
What happens in this case with this?
It's a very good question, because it's the next slide. Yeah. So okay. So it doesn't depend, and as I said, the first interpretation, it's an obstruction to fit all this data into a transitively algebra. Okay. So now let's try to do the same thing, okay, as I did before. I can find the slide. Okay. Okay, there are a few things that I want to say. No. Okay. So when should I stop? Because I don't know when I started. You know, someone else with in 10? 15, please. Yes, okay, 15. Okay. Right. Okay. Okay, at 30 I should stop. Okay. So you can interpret. Okay. So now I'm gonna. So if you take these three equations, you can actually interpret it as a map, right? I'm gonna write it like this. You can take nabla, omega, phi, and it goes to. So now I have to put, an extra copy of Z. Right. So you can bundle all of this into an infinity map. You can also do gauge transformation. You can. So if you have two, so phi prime, and here now I have a gamma and a beta. So all of this thing works with this extra term. Okay. Kind of obviously, I want to say. So what is interesting here is interpretation for this, because where this comes from, these are like higher derivation, which is why I put a point of the complex. So that would be GM with the Chevalier-Eilenberg, and then the wedge product. Okay, because these are degree 0 derivations. Okay. And these are degree -1 derivation. So degree -1 derivation will take one forms to functions, so it's a section of G. Okay, and so that would So that would be in the first case. What if you forgot about the Z? Okay, and actually, if you have the Z here, in order to interpret this thing as a derivation of something, you should do something like this. So you have like Gm, I would shift by 1, some Gm shifted by 2. Okay. If you interpret these maps, as some kind of, oh, I have a map, I'm going to use this to define a semi-direct product. So what would come out of this is, instead of a transitively algebraid, you would have a transitive 2 algebraid. Okay. And here the up. Okay. So use this map in order to define a semi-direct product of Tm acting on this guy. Okay. So all this works, and I have 5 minutes. So let's go to the interpretation. I mean, I have to talk about holonomy. Right. So up. Let me explain now how this, to somehow integrate this map, okay? Now what's the interpretation, holonomy of this thing, okay? So the idea is I want to integrate this thing here. And so we're going to take cubes. So I'm going to take the interval times 3, so really, and a map K with values in M. Yeah. So I have a cube inside M. Oh, sorry. But because I have a bundle of Lie algebras, at each vertices, I have a Lie algebra, and I can integrate the Lie algebra. So I'm going to have a Lie group, so Gx, Gy, Gz. So here things you have groups. Yeah. And each edge here defines a path in M, because I have this map. And I have the connection. So I can integrate nabla, and integration is the holonomy. Okay. So from here to here, okay, I have, a morphism from a Lie group to another Lie group. Okay. You should see this as a category, and this is a functor. Okay. Now, on each basis, okay, so I have a surface in M. So here, I have functors, and you can now integrate omega. And what this tells you is that when you compose the holonomies, they don't match because there's curvature. We know that the curvature measures makes it dependent on homotopy, but basically integrating omega, you can do natural transformation that each phase commute. And so what you obtain is some kind of a cube that is not commutative. None of the phases are commutative, but they are commutative up to natural transformation. Okay. And the question is about the phi. Yeah. And the way you interpret the phi is something like this. So there are two ways. Okay. There are two ways to go from bottom to top. Tack, tack, tack. And so this separates the cube into, there are front faces and back faces. So like this, up, up, up. So these are front faces and back faces. And here, same, so front faces. Okay. So front faces, back faces, But these are natural transformations. So you can compose this guy. So it should be something like this. So one natural transformation, another natural transformation, and the other one would go like this. Here's the same. I can take this natural transformation like this, natural transformation. A natural transformation composed horizontally, vertically. And there's a composition, so that would be sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. Okay. And so the interpretation theorem is something like this. Is that if you take the triple integral of phi along the cube, okay, so this is a z-valued free form. I can integrate, okay, and this measures, okay, because so this is the composition. So the holonomy is the composition of functors. Okay, so here I have a functor, another functor, and composing these guys have a natural transformation. Here they are the same guys, so the composition here, the functor is the same, and I have so one natural transformation, two natural transformation between the same functors. So, and because I'm working with a group, they differ by an element of the center. And so essentially what you can do is something like this. It's going to be sigma 6 composed with sigma 5 composed with sigma 4 composed with sigma 3, sigma 2, sigma 1, minus 1. Okay. And maybe I'm going to end with this. So that's the interpretation. It's kind of cute. And what this is Stokes. Why is this Stokes? Because what I'm writing is, remember, this is nabla omega. So I'm writing something like this equals, because integrate the way you will obtain this natural transformation by integrating each phase and combining. So here I'm making things a bit being a bit sloppy. Okay, and you can use this to prove interesting things, such as the Mackenzie class is aspherical. It's super easy because you take a free sphere, and the integration of the free sphere, you interpret it like this, except your cube, you know, you just collapse all the faces, and all these integrals are 0, and so it comes up right away. Okay, and we interact entering the homotopy. Thank you. Okay, I'm good with that. Yeah. It's free algebra. Yeah. Yeah, so I didn't have time. So one of the questions we were wondering with Pedro is how can we obtain phi as some characteristic class associated with the fiber? I mean, because you know you can look at the cross module of the fiber type, and so you have a class in the outer automorphisms with values in the center. And we suspect that, so if this class vanishes, automatically the Mackenzie class vanishes. So this would give a condition, you know, on just the fiber type, which is universal for a bundle of the algebras with inner connection. Yeah. Yeah.
So it's something that perfectly lives on the left-hand side. So it's possible to obtain that class.
So okay, we can do something like this. Okay, so you can take this as a cross module. Okay, and so there's a class which is in the out GM. So this is the co-kernel. You take derivation mod at G, and this is a transitively algebroid. Okay, and here you put what, the center, and you have this class which is canonical. And what we can prove, in fact, so the interpretation is, you know, the connection is inner, and you have a map. So that would be the projection. I would take my nabla, something like this. Okay, and you can compose with the projections, nabla bar. And because the curvature is inner, now this is a Lie algebra map. So I can pull back the class from here to here. And so it's easy to see that this is Mackenzie class. And basically what we do is we just forget to start working like this in this guy and try to find character, to write this guy via some Chern-Weil construction. It's difficult.
Any other question? just gonna put, I don't know, when I share my screen, I see nothing but the screen, so
Oh,
I was just waiting to, so
yeah.
I'll do that now, share my screen and then.
Okay, great. Anyway, thanks a lot for taking the time to speak here. Let's see next time in person. Anyway, so it's a great pleasure to have Krepski as a speaker now. And he will talk about inequality of infinitesimal symmetries of level curves.
Okay, thank you very much for the opportunity to speak and for the invitation. Can you hear me okay?
Yeah.
Okay. So thanks. I'll just get going. I guess the talk today, just to give you an outline of where things are going. I'll sort of start by telling you about a kind of a story in symplectic geometry, just to motivate kind of where the rest of it comes from, and so this will mean we introduce Lie two algebras and two-plectic manifolds very briefly. Really, we're just talking about closed freeforms, and then we'll discuss bundle gerbs and their infinitesimal symmetries and how Lie two algebras come into the picture there as well. Okay, so let's start with just reviewing a little bit about pre-quantization of symplectic manifolds. So remember that a pre-quantization of a symplectic manifold, one way to think of it is just a principal S1 bundle over your symplectic manifold equipped with a connection whose curvature is the symplectic form. So I'll ignore constants like 2 pi throughout the talk, and so this of course means that your two-form, so such a pre-quantization need not exist, but it would exist if your two-form was integral, right? So or integral periods, and this just means that its Durant cohomology class is in the image of the coefficient homomorphism from the integers to the fields. All right, so there's this well-known theorem by Constant that says there's a Lie algebra isomorphism, where so from the Poisson Lie algebra to the so-called infinitesimal quantumorphisms. So these are vector fields on your S1 bundle that preserve the connection, and so the connection essentially gives you this horizontal lift, and then you have to adjust by the function in the vertical direction here. All right, so then Constant shows you that this is a Lie algebra isomorphism. So there's another natural Lie algebra that you can associate to a closed two-form, namely the one on the screen here. So you just take vector fields and functions, and this is a natural bracket here, and there's a Lie. So here, essentially, you can use the same formula I just showed you, the one due to Constant, and there's a Lie algebra isomorphism to not vector fields necessarily that preserve the connection, but just S1 invariant vector fields. And since you're using the same formula to define this Lie algebra isomorphism, then you naturally get, so in the case when omega is symplectic, and you have Constant's isomorphism on the left side here, of course it's compatible, so you have this commutative diagram shown there. All right, so this is essentially the story that we'd like to generalize, and so let's now imagine that omega was a three-form and sort of see where this would go. Okay, so just recall quickly, two-plectic manifold will be a manifold equipped with a closed and non-degenerate three-form, and so we won't really spend too much time talking about these, but I'll just say that while there are lots of examples out there, notably though, semi-simple Lie groups, you can equip it with the so-called Cartan three-form, and they're sort of analogs of the cotangent bundle and so on. For us, really, we're only just going to use the fact that omega is a closed three-form now. But this is a good place to start our story. So in this setting, instead of Hamiltonian functions, one considers Hamiltonian one forms, and these would be one forms on the manifold that satisfy Hamilton's equations, right? And in the case where your simplex or your two-plectic form, your three form is non-degenerate, then this the vector field, if it exists, will be unique. So there's a theorem due to Rogers that says that these Hamiltonian one forms they form a Lie-2 algebra, okay, or if you like, they form part of the degree 0 part of the Lie-2 algebra. So so let's spend a little bit of time reviewing what that is. Okay, so the way I will view a Lie-2 algebra is the following way. So you want to think of it as a two-term chain complex. So of course this is just a linear map D between two vector spaces, but the chain complex language is helpful in describing the rest of the structure. So we will think of it as a two-term chain complex V1 to V0, equipped with a graded bracket, so a skew symmetric chain map, which you think of as being a bracket. It is skew symmetric, but it need not satisfy the Jacobi identity. So there's this thing, it's a great name called the Jacobiator, and it's a chain homotopy that measures the failure of the Jacobi identity to hold. So you have a few different ways to group brackets when you have three elements, and so this chain homotopy measures the failure of those two things to be the same. And if you have this homotopy, well, you can consider taking four elements and putting brackets on them in different ways and kind of applying this deformation of this chain homotopy. And so this chain homotopy has to satisfy a kind of coherence condition on fourfold brackets, okay? Which I won't write it down, like 10 things in the equation. So just we want to know that there is a coherence condition that must be satisfied. Okay, so here's our sort of a definition of the Lie-2 algebra, and what we'd like to do, well, let's look at some examples like this, right? So the first example is the one that's the analog of smooth functions on our manifold. So in this case, we recall we look at the Hamiltonian one forms, and as I said, it's sort of part of a Lie-2 algebra. It's the degree 0 part. Degree 1, we just put smooth functions. And the differential in this two-term chain complex is just the Durand differential. And the bracket in this case, the bracket of two forms in degree 0 is given there. And if you take the bracket of something in degree 0 with something in degree 1, it's just defined degree 0. And of course here we're using the three-form omega to define the bracket. And so this bracket does not satisfy the Jacobi identity, but does sort of up to D of something, and the something is this Jacobian here, which is given by the triple contraction of the three form with the three Hamiltonian vector fields x1, x2, x3. So as I said before, we can and we will drop the non-degeneracy condition so that we're just talking about manifolds equipped with three forms, and instead just use pairs where consisting of a vector field and one form for which that one form is Hamiltonian with vector field x. So the only difference now is maybe the vector may not be unique. All right, so that's one of the analogs of our story. So now we have an analog of the smooth Poisson algebra of smooth functions, this Poisson Lie-2 algebra of so-called observables. And the other Lie-2 algebra that we saw, its analog will be this sometimes called this Atiyah Lie-2 algebra. That's what I've seen it called. So so it's also given by smooth functions in vector field, but now you kind of split them up into two pieces, and the differential is just 0. So it kind of looks uninteresting. And in this case, the brackets are given exactly by all the natural operations in front of you. So the bracket of vector field is the Lie bracket. You can take the bracket of the vector field with the function, it's the Lie derivative. And of course, the bracket of vector field satisfies the Jacobi identity on the knowns. But what's sort of interesting here, I guess, is that you can still introduce this Jacobiator to be against this triple contraction, and because the differential is 0 here, it's kind of like hiding in the background. So and then you can check that the consistency condition or the coherence condition of fourfold elements is just the condition that omega is closed. Okay, so and now we have a third example in this case, which is kind of like an intermediate example between the previous two. So associated to a closed three form, we can look at the exact Courant algebroid with brackets given by the twisted Courant bracket, so twisted by this three form omega. And it turns out, by a result of Reudenberg and Weinstein, that the sections of this Courant algebroid give you a Lie2 algebra. And so here's the bracket, and in mixed degree it's also basically given by the derivative. And the Jacobiator here is sort of quite different. It's given by well, it uses the symmetric pairing on the generalized tangent bundle. Okay, so by the way, here plus CP just means plus cyclic permutations. Okay. All right, and then one more example about excuse me, of the Lie2 algebras comes from just looking at multiplicative vector fields on Lie groupoids. So I probably don't need to remind this crowd of what a multiplicative vector field is, but let's quickly just say it. So if you have a Lie groupoid G, and you can consider the tangent bundle as a Lie groupoid, and a multiplicative vector field will be given by a pair of vector fields on the arrows and the objects that defines nanofunctor. So it defines a Lie morphism from G to TG. So of course it's a section, but the important point here is that it's compatible with all the groupoid operations. Okay. So multiplicative vector fields by sort of independently by Berg, Evans, and Lerman, and Ortiz and Waldron, they form part of again, so the degree 0 part of strict Lie2 algebra. So strict here just means that the Jacobiator is 0. And in degree 1 here, we have just sections of the Lie algebroid, and the differential is given by the anchor map, so that's the part in degree 0, and objects, and the sum of the left and right varying vector fields associated to the section of the Lie algebroid. So bracket in degree 0 here, well, it's just regularly bracket, but then you can take the bracket of multiplicative vector field with the section just by taking the right invariant vector field associated to A, and you check that the bracket of x1 with A is also right invariant, and then so that defines a section of the Lie algebra. Okay, so that's an example of a Lie2 algebra, and we will use this one quite a bit. Okay. All right. So the next thing we'll talk about is introducing bundle jerks. So in case it's not sort of part of your everyday life, we can review that now. And the way we'll introduce them is by starting with an example. And the example is what's known as Hitchin jerk, or bundle jerks that you could build out of check data, so out of like open cover data associated to an open cover. And this should be thought of in analogy with trying to construct a principal bundle using transition functions, right? Using transition functions on some open cover. Okay, so let's pick our open cover and consider the covering groupoids associated to it. So the arrows are just elements in the intersections, and the objects are just elements in the cover itself. And we'll pick a principal S1 bundle over the arrows here. And since we chose a good open cover, we may as well pick an S1, pick the bundle to be trivial, right? So it's a good open cover. And what we'd like to do next is define a groupoid multiplication on this principal bundle, on this trivial bundle, that covers the one coming from the covering groupoid here. So such a multiplication will have this form. So where xij here, say, denotes the element x in the manifold belonging to the intersection, uy intersect uj. And zeta and eta here are just elements in S1. So then your groupoid multiplication will have this form, but you can kind of twist the regular multiplication on S1 by this S1 valued function g on triple intersections. And if you want this to be a groupoid multiplication, you want to be associative in particular, and associativity forces this S1 valued function g to be a 2 cocycle. Okay, so what you get here ultimately is a class in degree 3 of the manifold with integer coefficients. And so we view bundle gerbs as kind of being the degree 3 analogs of S1 bundles in analogy. Analogous to this would be analogous to the Chern class of an S1 bundle. All right, so this example essentially tells everything we need to do to define bundle gerbs. So let's now kind of repeat this, but in slightly more general setting. So an S1 bundle gerb then consists of a surject, so the data of surjective submersion over M, so not necessarily given by an open cover, but you have some surjective submersion. And we can form the submersion groupoid. And what we'd like to do now is pick a principal bundle over the submersion groupoid. And we want that bundle to have equipped with it a groupoid multiplication. So it has to have groupoid structure. And that structure covers the one on the submersion groupoid. And further, the F1 action on P has to be compatible with the groupoid multiplication in the following sense. So here the dot refers to the F1 action on P, and concatenation is just the groupoid multiplication. So you can slide the elements of S1 sort of in this way whenever you can compose arrows to begin with. Okay, so such a thing, if you're familiar with these things, what we're really looking at here is a central F1 extension of groupoids of this submersion groupoid. Okay. So now we can say, well, we have a groupoid in front of us coming from a bundle gerb, namely the bundle gerb itself, the central extension. And so naturally, its multiplicative vector fields give you an example of a Lie-2 algebra. And maybe just as a quick sort of aside, one can view this example as being the analog of the Atiyah sequence or the Atiyah algebroid construction. So this appears in a recent paper by Herrera, Carmona, and Ortiz, that if you view S1 bundle gerbs as a two-group bundle and try to mimic the Atiyah algebroid construction, then you just get back looking at vector fields. So let's just quickly recall what that means. So if you take this S1 bundle gerb, so the underlying groupoid P, and just look at its tangent bundle. And then now what you would do next is you would quotient by the group, or quotient by this two group in this case, which just means you're going to quotient the arrow spaces by S1. And when you quotient the arrow spaces by S1, the base is just the submersion groupoid again. And so what you end up with is a vector bundle, a BB groupoid, where both the vertical arrows are Lie algebroids, right? The one on the right here being the Atiyah algebroid for the underlying principal S1 bundle P, So such a thing is an LA groupoid, and by this result we mentioned before, its multiplicative sections form a Lie-2 algebra. You can check sort of fairly directly that this Lie-2 algebra section is just the multiplicative vector field on P. I'm being a bit sloppy in notation, by the way. Sorry, I'm pointing to the screen like you can see me pointing. I'm being a bit sloppy in the notation in that when I write here, x of P, that's strictly speaking, that's the degree 0 part of the multiplicative, the Lie-2 algebra, but sometimes I'll refer to the entire Lie-2 algebra just by talking about its degree 0 part. Okay, so we have another example of the Lie-2 algebra under our belt, and now we can talk about connections, so connection data on bundle gerbs. So just like S1 bundles, there's sort of theory of connections and curvature and so on. And so in this case, a connection is given by a multiplicative connection, so a connection form on the underlying S1 bundle. And it has to be multiplicative, or if you like, just compatible with the groupoid structure on P. And in this setup, we can also define something called a curving. And so a curving is a 2 form now on X, on the subversion of our gerb, that is also compatible with the groupoid structure in the sense of this relation here. And then one can show that given the data of a connection and a curving, there is a unique 3 form on the base manifold M that pulls back to dB. So dB is basic just by these relations, and that 3 form is what's known as the 3 curvature of the connection. Okay, so you can think of the connection data, like it may be useful to think of data in terms of this double complex that you can build out of the simplicial manifold associated to a Lie groupoid. So that connection then lives here in degree, total degree 2. And being multiplicative means that its simplicial differential is 0. So the simplicial differential is just, in this case, pulling back by source, target, and multiplication, and you just alternate the signs. And then the curving lives here in degree, or by degree 0, 2, if you like. It's 2 forms on X. And then this relation that B and gamma have to satisfy just means that the simplicial differential of B agrees with the direct differential of gamma. So it can be helpful to kind of imagine connection data given in terms of this this double complex. All right, so we have now our analog of an S1 bundle. It's an S1 gerb. We have the notion of connection. And remember when I first started talking, I was talking about infinitesimal symmetries of a prequantization that preserve a connection. So here we'd like to consider infinitesimal symmetries of the bundle gerb that preserve the connection data. Okay, so so the symmetries are multiplicative vector fields. So multiplicative vector field will say it preserves the connection data, it preserves the pair gamma B. While it doesn't have to preserve on the nodes, but it does up to some 1 form alpha. Okay, and so we'll go back to this double complex in a second. But just before that, note that for any multiplicative vector field on such a Lie groupoid will descend to a vector field on M, just by virtue of having a multiplicative vector field here on X. And if you can show easily that if it's a multiplicative vector field that preserves connection data in the sense, then it would have to preserve the 3 curvature on the nodes. Okay. So just going back quickly to our double complex here, if you look at the Lie derivative of the connection data, it lies in total degree 2. And using the defining characteristics of what gamma and B satisfy, so the relations that B and gamma satisfy together, the fact that gamma is multiplicative, you can show that this gives you a total closed or a closed element in the total complex. And so saying that the multiplicative vector field preserves the connection data is just saying that that this Lie derivative here is totally exact. Okay, so it's kind of a natural condition to impose in this. Okay, so together with former postdoc Jennifer Bond, we showed that connection preserving multiplicative vector fields form a Lie-2 algebra, sort of basically inherit the Lie-2 algebra structure from the Lie groupoid, and you just tack on this one form alpha that witnesses the fact that the multiplicative vector field preserves the connection, and the differential is given there, and the bracket is also sort of more or less near already. So yeah, here again the differential is given in terms of the anchor map of the Lie algebroids of P, and this is just telling you that the differential of an element in the algebroid, it is of course a multiplicative vector field. We knew that already, but it also naturally, automatically preserves the connection, and that this would be the connection form. So you have a kind of natural choice of alpha, if you like, for a given A. All right, so we'll denote this Lie-2 algebra by Q, and this is what we might think of as the infinitesimal quantumorphisms, or the infinitesimal symmetries of our bundle gerbe that preserve the connection. And so let's look at a quick example here. So let's talk about the trivial gerbe. It's kind of a trivial example, but instructive on where we're headed in a second. So you can take for a gerbe you can take X to be just the identity map. So your submersion is just the identity, and then P will just be the trivial S1 bundle over M, and equipped with the trivial connection, and B is just any two form at all. And in this case, a multiplicative, so then you can check that the trivial connection with B is indeed a gerbe connection, and then in this case, the multiplicative vector field is just going to be a vector field on M. And that vector field will preserve the connection data precisely if it preserves B in this kind of weaker sense. Okay. So then, in just with reference to the previous slide, the so-called infinitesimal quantumorphisms, right? This Lie-2 algebra is just going to consist of sections of the generalized tangent bundle that have to satisfy this relation here. And the bracket is kind of the natural one as well. So I'm just showing this example in particular because if you look at it, you can see that if I chose an infinitesimal symmetry that preserves the connection, I can form from it just by this sort of shearing map. I can form a Hamiltonian one form that corresponds to the vector field U, right? And so that turns out to give you a map now. The infinitesimal symmetries preserving the connection to Hamiltonian, the Lie-2 algebra of observables of the manifold M with the three form DB. Okay, so in this case, we get an automatic isomorphism of Lie-2 algebras, and then it turns out that this example kind of generalizes in an appropriate sense to non-trivial gerbes as well. Okay, so so now I'm talking about comparing Lie-2 algebras. I'm talking about morphisms of Lie-2 algebras. So let's quickly review that. So if I had two Lie-2 algebras, two-term chain complexes with bracket and Jacobiator, then a morphism of Lie-2 algebras will be, well, it'll be a chain map, so a map that's compatible with the differential. And this map need not preserve the brackets, but there can be now a chain homotopy that tells you the failure, that measures the failure of this map to preserve the brackets. Okay, and sort of as before, if you now introduce a chain homotopy as part of the data, well, there needs to be some sort of coherence with all the other chain homotopies floating around. So you need some coherence condition with the two underlying Jacobiators, and this is it here. Okay, so just to give you a sense for how this naturally comes up in this discussion, so mention quickly, we now have morphisms in our morphisms of Lie2 algebras, but there are also two morphisms which we won't really talk about, but I'll just mention twice that there are two morphisms in this two category of Lie2 algebras. Yeah, I'll just leave that there. So this story, or this setup of bundle gerbs with connection, sort of naturally admit the discussion of Lie2 algebra morphisms in this sense. So in particular, so for example, if you consider the multiplicative vector fields on the submersion groupoid, so this is basically just vector fields on X, you can use the connection to lift the vector field on X to a vector field on P, on the groupoid P. And of course, it's a linear map, and we wouldn't expect this to preserve the bracket. However, you do have this other data of curving, and you can use the curving to kind of measure the failure of this map to preserve the bracket. Okay, so it turns out that B induces the corresponding chain homotopy for the chain map here. And you might think, oh, this is great, I've got a Lie2 algebra morphism. However, you don't necessarily get the coherence condition unless the corresponding 3 curvature of the bundle germ vanishes. So this is entirely analogous to the situation for, say, for principal S1 bundles, where horizontal lifting wouldn't give you a Lie algebra map unless the connection was, or unless the curvature was 0, unless the bundle was flat, right? Okay. So the appropriate setting for us will be to not to use the Lie2 algebra morphisms that we just discussed. So I'll sort of switch it on you now. We'd use a more general notion, or what you can think of as a generalized morphism of Lie2 algebras. Okay, so strictly speaking, what we're doing here is we're localizing the two category of Lie2 algebras with respect to quasi-isomorphisms, which is to say chain maps that induce isomorphism on homology. And we'll do that using the mechanism of butterflies, which is due to Newton. So a butterfly is this lovely thing here. It's a vector space equipped with a bracket, and you have these 4 structure maps to the two Lie2 algebras. So this is kind of an intermediary, and the bracket is Q-symmetric, and it has to be compatible with all the rest of the structure in the following way. So first is that the 2 diagonal sequences have to be chain complexes. Okay, so just to say that composition one way is 0, and as well, the composition the other way. So the red, and hopefully shows up as red for you guys, but the north, east, southwest sequence will have to be short exact. So that's kind of what determines then what the direction is of this generalized morphism. The structure maps also have to be compatible with the brackets. So in more or less the sense that you would imagine. So for example, sigma and rho, the 2 bottom maps here would have to preserve the brackets. And the bracket on E need not satisfy the Jacobi identity because, well, we don't expect any of the brackets ever to satisfy the Jacobi identity, but they do have to be compatible with the 2 Jacobiators given on B and W. Okay, so this is the notion of generalized morphism that we work with. And so it turns out, if you, it so happens that the butterflies that are invertible are the ones sort of corresponding to quasi-isomorphisms in Lie2 algebras with ordinary morphisms. Just what it means to localize our category. And so it's helpful to know when you have a butterfly that's invertible, like how do you formally invert, and it's invertible if the other diagonal sequence is also short exact. And then you can just obtain the inverse of a morphism just by switching B and W, switching the wings of the butterfly, if you like. And so the second time I'll say it, I guess, but maybe not surprisingly, Lie 2 algebras with butterfly morphisms, a 2-category, and notice here the composition. I'm not really going to show it to you, but I guess the composition is given by kind of fiber product construction, and so the composition wouldn't be strictly associative, but it'll be associative up to some 2 morphisms. Okay. All right, so now we can sort of finally get to the punchline, I guess. So suppose you have a bundled gerbe with connection and 3 curvature omega. Then then we get 3 invertible butterflies that connect the Lie 2 algebras that we introduced. So going from left to right, the Lie 2 algebra of observables. This is kind of like the analog of C infinity of M for symplectic geometry. In the middle, we have the sections of the Courant algebroid. And on the right side, we've got the so-called Atiyah Lie 2 algebra. Remember, this was the 2-term, or the Lie 2 algebra with 0 differential with vector fields on degree 0 and smooth functions in degree 1. And so we have invertible butterflies to the sequence on the bottom and on the left, again, going from left to right. So we start with the infinitesimal symmetries, or if you like, multiplicative vector fields that preserve both connection and curving. In the middle, we've got, so essentially the same thing, connection, preserving multiplicative vector fields, but now that don't necessarily need to preserve the curving. So, so we just drop that condition entirely, and the same formula give you a Lie 2 algebra there. And then finally here we just have multiplicative vector fields, which again we might want to think of as being the analog of what you get from trying to apply the Atiyah algebroid construction on S1 bundle gerbe. And up top, the morphisms R and S are, say, appear in the work of Rogers and his collaborators. But I'll just say the sort of the natural ones. So think of the elements in degree 0 here. Well, here you have the
No geral, YouTube. Pode usar o celular. Mas aqui não pode apontar que atrás tem internet. A internet está funcionando aqui. Essa rede ali. Ele está conectado naquela rede.
Botei algum celular aí.
É você? Talvez não. Pode trocar quem está aqui por aquela. Pode ser, pode ser.
And there's also a paper by Sebastian Würzbach that shows a similar result for this Lie butterfly E. And well, and I'll just say that it depends on some further choices, like the kind of bundle you're using and a sort of arithmetic connection as well. But the benefit of having those extra choices is that you get honest Lie to algebra morphism instead of something general here. Okay, so let's see, how am I doing on time? Do I have maybe like another couple minutes?
Yeah.
Yeah. Okay. So now I just want to quickly go through an idea, the main idea, I guess, of the proof here, only because it's kind of so easy. So imagine we wanted to construct a map from. Sorry, I think I'm getting an echo here, so I'm just going to turn down the volume. So imagine we wanted to construct a map from a multiplicative vector field that preserves the connection to a pair consisting of a vector field on M that is Hamiltonian. So you can sort of start off by essentially taking your multiplicative vector field, again, realizing it descends to a vector field on M. And then you might kind of try some naive things and say, well, maybe I'm lucky. Maybe this vector field sort of is automatically Hamiltonian, and I can guess the Hamiltonian one form. And here it looks like maybe you are lucky, except this form, this alpha minus the contraction of B and U, this need not be basic, so it need not descend to M. So kind of on X, it looks like you've solved the problem, but on M, you haven't necessarily. And if you look at the kind of the abstraction to this form being basic, it's encoded in the vertical piece of the multiplicative vector field, or the arrow part of it. So so then this gives you a way to adjust, your sort of your initial guess, because the connection is multiplicative, then this vertical thing is basic. And well, maybe not basic, but it's like it descends to X. And so then this gives you a way to adjust your guess from the initial guess, say, of alpha minus the contraction to alpha minus the contraction minus this correction term, which depends on the vertical part. So all this to say is that, well, if you were sort of naively looking for a map from multiplicative vector fields that sort of connection to Hamiltonian one forms, and you could try to do it this way, but of course this doesn't give you a map because you have to make a choice of G, right? You have to make a choice of primitive. But that's where this sort of the beauty of the butterfly is that the butterfly holds all the choices of G for you. So you just stick in the G as part of the data of the butterfly. And then now you're able to, of course, project to both sides, and you just need to define a bracket to kind of check if this works. But that's kind of like, I think, the underlying philosophy of these butterflies, that you kind of add in all the extra choices you might need to make if you were to naively construct a morphism from one side to the next. And yeah, just to say that the two other butterflies, they kind of work similarly. So anyways, I'll stop here. Thanks very much for your attention.
Can you hear us?
Stuff that was mentioned.
Can you hear us?
Yeah, I can hear you.
Are there questions? So I have a general question. By chance, I'm hearing myself.
Sorry, I don't know how to. I could mute my speaker, but then I couldn't hear you. Oh, maybe I can. Yeah, maybe I can mute the microphone. That was me.
I was just saying that last week I heard a talk by someone called Miti, I think, about a paper with Mark Sambon that somehow reminded me a bit of this story that we're talking about. But without the integrality condition of the three forms, they phrase things in terms of higher current algebroids and infinity morphisms instead of just butterflies. Do you know the connection is right? Just out of curiosity.
I need to turn the microphone back on. So yes, so I'm aware of this paper. Let's turn down my sound so it's better for me anyway. I'm aware of this paper, and part of a connection at least is in, I took down the slide, but in the slide with that this work with my PhD student Dina Mojimbuna. So there is a way to relate. Yeah, so there's no integrality condition, and then there's certain, let's just say, a certain morphism of Lie two algebras that holds integral or not. And this is kind of like the top row in that last slide with the theorem that I just showed. So the Lie two algebra of observables going to sections of Courant going to this Atiyah Lie algebra. So that's like the top row in the diagram, and you can do this in higher structures as well. And if you then want to play some games like trying to say change the form, the three form by what I think is sometimes called like a gauge transformation or a B field transformation, then you can say, well, now how does everything relate? Does everything kind of play together nicely? And the answer there is yes, when you can. So, you wouldn't expect that the Lie two algebra of observables be the same as, for a given three form, be the same as the Lie two algebra of observables for the three form, say, plus dB. Just like you might not expect a similar thing for, say, symplectic geometry, right? If you change the two form by something exact, it's sort of not really a natural way to compare. But if you pull back to, say, a Lie algebra that is acting on the manifold, if you restrict to an action of the Lie algebra, essentially, like restrict along a moment map, then you can compare. And that's one thing that this paper of Miti and Zambon does. And then in the bundle gerb sort of butterfly language, we do this as well with Dina.
Any other question? So let's thank Garrett and Ben.
And thanks as well for working all those technical things. I'm sure it's stressful at the time.
Well, thank you. Next time.
That would be awesome. Great. Thanks, everyone. Enjoy your lunch.
Which